Hello, welcome to another problem session. Actually, today we are going to talk about some conceptual things, and then later on we can do a lot of problems. Okay, so problem concept we want to talk about today is stress and strain. Now, we want the address these concepts go with the question that if I have an object and I deform its shape, then how do I take into account what happens inside the object, etc. So the simplest object is say you have a spring. You learned that you can deform the spring in this way. So one way we do it is like, okay, this side you attach to some very large body, so m is infinite, but on this side I can hold it by hand and pull on it. So this is my hand, I pull on it, so the spring extends 1 2 3 4 5 6 7. So 1 2 3 4 5 6. It gives this it gives the number of turns, but it became longer now. So my hand is now here, and you can see at this point, and I don't do anything stop. So there is a this much is the change in length. So this is and that used to be length L originally, and this is the change in length. The strain is this ratio of this, we'll call it strain. Strain is the fractional change in length. So this is a strain of a spring. Well, what happens in the spring, you know that in order to maintain this strain or change in length, in order to maintain this change, I need to be applying a force, right? So I'm applying a force. This is force by me on a spring, right? So if you look at on this end, it's actually a spring is applying, this block is also pulling in this direction, F by support on spring. So a spring has two forces, and there's no acceleration of this spring is 0. So if I were to take the spring as m spring, acceleration is spring, and this is the x, this is the x-axis, equals to F net on a spring. There will be this force and this force, and so this side is going to be 0. So these forces will be equal and opposite. So F by me on a spring will be F into some magnitude, F by support on a spring. And now let's look at what happens to the spring. Actually, the spring itself will also apply a force back on me. So there will be a force of same amount. Let's call this F. Is same amount. There will be F by a spring on me, and there will be force by spring on support. these are pair forces, right? So equal and opposite forces, those are pair forces. So when you deform the spring, a spring starts to apply a force. So lesson here is a deformed spring applies force at both of its ends. So that's the lesson. Now this is related to what we call stress, and here the stress is actually you don't use the word stress here, you use the word force only here. But when we have a material, this thing that the spring applies a force when it's deformed gives rise to a concept of how to take into account whole bunch of springs and whole bunch of forces. How do I put them together into one quantity which we assign to the material, and that will be stress. So let me give a model of the material and think about changing the shape of the material, and there will be a response that I should expect and how to quantify the response. Okay, so we're going to look at the material as a material. Say I have a block material, I have a rectangular block like that. I have a rectangular block, and we suppose I fix this end, maybe a wall or something. I just fix this end somewhere. So this is fixed to this wall. So this is wall, and there's not a lot to move. That's like a m equals to infinity on this side. So the model of the material would be like this thing is made of a whole bunch of springs. So say, assuming there's one spring here, one spring here, one spring here, spring. So you can see I'm going to model it. When I pull this, when I pull this end, I hold it and pulled it. What will happen is when I let go, it goes back. So all materials have this property that when you pull it, so number one, pull, and then not too much, just a tiny pull, then this will become a little bit longer. So this is the delta L, and used to be L on this side. So let's call this is the X direction I'm going to pull. So Lx this side and delta Lx. So I pull, so delta Lx is much smaller than Lx, so very tiny amount, and let go. We notice that it goes back to its original. So it notice that goes back to Lx. So this is called elasticity. This tendency is called elasticity. We say the material is elastic, but if I pull it a lot, it gets deformed. So we also notice that pull a lot, delta X not too small, then gets deformed forever. So that's also we notice. So the model of it reminds us of a spring. The model is to think of material as a whole bunch of springs. So when I pull it, just like a spring, it goes back to its original shape. But here we can think of this as a spring, whole bunch of spring lined up after one after another, and the spring got pulled and then pulled back. So we can say that because spring, we learned that. So here is something was pulling. So this is the F pull over this surface. So you can definitely see that, right? That you will get this spring will pulling back, and so this will be pulling back, this will be pulling back. So how many springs are there? We really don't know. I mean, this material, this is a model, so this is very large number of spring across this surface. So let's call this surface, this Lx, then this let's call Ly, and this let's call Lz. So across this area, Ly, Lz, this is the area. Across this area, there are a whole bunch of springs, and each get pulled, and so they're each applying the force. So all we can say is how much force their forces must add up to what I pulled with, right? So F pull applied by someone, some agent on the, let's call this guy just as for simplicity a rod, on the rod. Then third law will say that these springs was gonna will say these springs will apply back on this side, this amount of force. Apply back if pull amount of force on that agent. So what's the upshot is across this area, it's being that much force is being applied across this area. So the quantity we want to say is deformation of delta Lx over Lx is means there will be a force by the deformed object per unit area. So would be F pull per unit Ly Lz. So this quantity is called stress inside the rod, deformed rod. Okay, so let me clean this up and clear out these definitions. So whenever conclusion is there is a stress F over area which is perpendicular to the direction it was pulled, right? Whenever there is a body, whenever a body is deformed. So you have F over area. We usually use the denoted by symbol sigma. So this is the stress. Sigma is this, that's the definition, and strain is amount of change, but that's not amount, fractional amount of change in the direction, right? So this is we just call it maybe epsilon for this strain. So if you now, the more stress you'll have, the more strain you'll have. So if I were to study how much stress I caused and how much strain it went, no stress, there's no force, right? So there's no, it just up to a point. So this has to be small. Okay, this has to be small. If it's too large, this doesn't continue forever. It can after some stress, it might just break, right? Permanently deform, maybe breaks here. So there is a range of applicability of this idea that they will be proportional to each other. So we can write proportionally by sigma proportional to stress is proportional to strain, which kind of like F is proportional to delta Lx, right? In the spring, one spring. If you have one spring, you have this case, but here material has infinitely many number of springs, so we just can talk about force per unit area, not force. So sigma is proportional to the strain, and equality is called Young's modulus. It will be Y is some constant, Young's modulus of the material. So this is one way you can deform it, right? So this is one. So suppose suppose you had steel, it will depend on the material. If you steel, you'll have one number. It also depends on temperature. So Y depends on material and the conditions, thermal conditions that you find yourself. Like some materials, when you heat it, it's easier to stretch than at lower temperature. So this may depends on temperature. And this is only when we are stretching it. So Young's modulus, when you're stretching it, it may have one property, and when you're trying to compress it, it may have a different value, or it may be symmetric. So might depends on stretching or compressing, may not be symmetric. Okay. Now there may be other ways you can deform it, right? So, okay, so if there's stress in this direction, so this is like we just talking about in X direction. Now, if you look at what's the stress along the Y direction, so this was the Y direction, but there's no force there. So, sigma along the Y direction is actually 0. What's the stress along the Z direction? Z direction, sigma along Z direction is 0. Epsilon along the Y direction is 0. Epsilon Z direction is 0. So in here there's just all the X directions. So these are like X direction, stress along the X direction, epsilon along the X direction. So you can think of sigma being have a direction on which it is acting. So you might say stress that's acting on this face. So stress that's acting on this face, which is pulling this whatever is holding in there, and there's a stress acting on that face, this stress acting on that face, this stress acting that, and that face and that face. So along all 6 faces, but here the only one that matters is stretching here, right? Now we could actually do other kinds of stresses, right? For instance, you could cause a stress, or you could change the shape some other way. Like suppose you had a some kind of jello-like material. So this is jello, squishy material, and you glued this part, maybe glued this part to some table, and what you did was you tried to push at the top. What do you think happened? This will actually, it will be like this. It will maintain its bottom contact completely, right? And it will actually change by an angle theta. So a strain here is actually this angle theta, which say, you know, if I have this height h and amount I stressed over here is delta say x, so this will be tangent theta will be delta x over h, and if delta x is small, this will be very small angle, so this will be tangent theta will be almost equal to theta. So this will be delta x over h. Well, clearly there will be a strain that there will be stress that whatever is pushing, say if you are the one who is pushing that way, agent is pushing that way, whatever the stress got developed inside is going to push on the agent back same amount of the force, right? So you can see that this force, the force of the agent, will be matched by this in order to maintain this much strain, and that will be stress will be computed per unit this area, say this A. So this stress here will be this force that being spread over this whole area will be equal to the force of the agent spread over this whole thing. This is the magnitude over this area that we just draw it like that. So now this will be the stress and this will be the strain. Again, this sigma will be proportional to sigma will be proportional to the epsilon again because of what we call Hooke's law. This is Hooke's law. When sigma is proportional to the epsilon, this is called Hooke's law. And we but we have different names for stress and strain now. So here is a page from my physics bootcamp website that goes over more detail, and you may want to consult that. So consult physicsbootcamp.org for so this kind of stress that causes angular, this kind of shape change is a different kind of stress than this. So this is shear stress and shear strain, and this is because I'm extending it is extension stress, and because it's caused by extending, so this is extension strain. And all of these laws will be, stress will be proportional to strain no matter what type you write down. We use a different symbol for here, and to be consistent with the website, I'll use letter G for it. And so this is the Young's modulus, and this will be called shear stress modulus, or simply shear modulus. This is usually for the same material less than that. Now there is another kind of stress that comes up. Okay, so consider here is like a deep sea, and you have some container in the deep sea, and this is very high depth and very high pressure. Pressure will be pushing on this and changing the volume of this thing. Maybe volume becomes a little bit less. Okay, so here's a volume change. Strain is a volume strain. Okay, volume strain will be change in volume over how much volume we have. The strain will be always dimensionless. So when we have epsilon equals to theta, this theta is in radians, and this epsilon was delta L over L, so it's dimensionless. Okay, so volume strain, or sometimes called bulk strain, because you're changing this whole bulk of the material. So the material is this container, and stress, we'll call it bulk stress. So sigma, which will be opposite of these forces, right? Opposite of these forces from outside. So this stress will be pushing it outward to whatever is pushing it in. So here it will be water. So this will be pushing on back on the water. So this stress, we'll just call it sigma. And again, so we'll call this epsilon. So sigma will again be proportional to epsilon. This is the bulk stress, and this is the bulk strain. And then there will be a modulus. We can call it letter B for bulk, just like that, bulk modulus. It's the same type of formula, right? But the stress and strain the strains are very different, and the corresponding stress associated still is whatever this force is per unit area. So this is sigma is still amount of force per unit area. Okay, so now we covered three types of stress and strain. That's on this page. Let me summarize in a clean way. So here is a summary of the three types of stress, and this is a Young's modulus. And this is shear modulus, and this is bulk modulus. So we're going to use this in the problems in the next lecture. So I'm going to stop here.